Every single day, you trust your clock. You operate on the assumption that time is a rigid, straight line, moving at the exact same speed for you as it is for everyone else on the planet. Following Isaac Newton's theories, humanity spent centuries believing that an hour measured on Earth was exactly 1 hour everywhere else in the cosmos. Albert Einstein dismantled that assumption. He proved that space and time are not separate entities operating independently. Instead, they are woven together into a single, flexible fabric known as spacetime. Imagine a massive, tightly stretched trampoline. If you place a heavy sphere directly in the center, the fabric sinks down under the weight. Gravity is the actual physical curving of the spacetime fabric. Because of this curve, time physically runs slower near heavy, massive objects. Time is not a universal rule. It is a highly flexible illusion dictated entirely by mass and gravity. To see how personal time really is, imagine you have an identical twin. You stay right here on Earth, while your twin boards a hyper-advanced spaceship and travels across the galaxy at near the speed of light. When your twin finally returns home, they are still young, while you have aged into an incredibly old person. This happens because an individual's personal experience of time depends completely on how fast they are moving and how much gravity is pulling on them. But if gravity has the power to stretch and bend time, what happens when that gravitational pull becomes so extreme it breaks time completely? When a massive star slowly runs out of nuclear fuel, its outward explosive energy disappears. Without that outward push, the star collapses under its own unimaginably heavy weight, shrinking down into a point of infinite density. This creates a black hole, an object with a boundary known as the event horizon. Think of the event horizon as the edge of a cosmic waterfall. If you drift too close, the gravitational current becomes stronger than your maximum ability to escape. Once you cross that invisible boundary, absolutely nothing, not even light itself, gets out. Because the gravity is so extreme, the pulling force at your feet would be violently stronger than the pulling force at your head. You would be stretched out like a long, thin string of pasta, in a gruesome process scientists literally call spaghettification. You would be torn apart at the atomic level before you ever reached the center, the singularity. The singularity is a point where density becomes infinite, and all known laws of physics cease to exist. For decades, the brightest minds agreed that black holes were immortal cosmic vacuums. Any information or matter that went in was permanently destroyed, creating a massive paradox that violated the established rules of science. In the 1970s, a theoretical physicist named Stephen Hawking proved mathematically that black holes are not completely black. To understand his proof, we have to look at the bizarre rules of quantum mechanics. Quantum mechanics is the branch of physics governing the microscopic scale. At an atomic level, empty space constantly bubbles with pairs of tiny particles that pop into existence and instantly destroy each other. If this pairing happens precisely on the event horizon's razor edge, one particle falls into the black hole while its partner escapes. To an outside observer, it looks exactly like the black hole is spitting out glowing radiation. Because of this slow energy leak, known as Hawking radiation, black holes slowly evaporate over trillions of years until they shrink and violently explode. This mathematical proof finally forced the massive cosmic rules of gravity to link directly with the microscopic rules of quantum mechanics. We know black holes eventually die, and we know our universe is constantly expanding outward. But this ongoing expansion raises a profound directional question. Why does time only flow forward? Why can we vividly remember the past, but we cannot remember the future? The answer lies in the thermodynamic arrow of time. It is governed by a strict law known as entropy. Entropy is a scientific principle stating that the physical universe naturally and constantly moves from a state of order to chaos. Physical matter naturally breaks, ages, and decays. The scattered shards of a broken cup will never spontaneously organize themselves and leap back up onto the table. The biological act of forming a memory requires your brain to consume physical energy. This process generates physical heat, which directly increases the total amount of disorder in the universe. You can only remember the past because the physical machinery of your brain is forced to align with the universe's relentless, irreversible descent into disorder. Rewinding this cosmic expansion back to its starting point brings everything to a single, infinitely dense moment, the Big Bang. This leads to the question of what existed before time itself began. Hawking proposed an answer using a geographic analogy. If you point at a globe and ask someone, "What is further north than the North Pole?" the question is completely meaningless. There is no spatial concept of further north beyond that exact location. By applying the strange rules of quantum mechanics to the entire universe, Hawking introduced the no-boundary proposal. He utilized imaginary time, a mathematical concept that treats time like a physical direction in space, to suggest that reality is a completely self-contained entity with no edges, no boundaries, and no specific start or end. If the universe has no true boundary, it simply is. It wasn't officially created at a specific point, and it won't be destroyed. This removes the physical need for an external creator to wind the cosmic clock. The physics of space-time suggests two primary realities. First, your perspective is entirely relative to your specific position in the cosmos. Second, entropy dictates that order is a temporary state. Maintaining any organized system requires a continuous input of energy to resist the natural slide into chaos. Right now, the greatest minds on Earth are hunting for a theory of everything. They are trying to find a single mathematical framework that unites the immense gravity of galaxies with the microscopic vibrations of quantum atoms. We live on a tiny rock, orbiting an average yellow star, sitting at the very edge of just one galaxy out of billions. Yet, through the sheer power of human curiosity, we have decoded the hidden language of space-time and mathematically dissected black holes. Discovering a theory of everything would provide a complete understanding of the universe's mechanics and the fundamental reason for its existence. In that moment, the universe will have finally understood itself.